Alrighty, good morning, guys. Can you hear me? How are we doing? Are there any questions before we get started on today's lecture? Okay, then let's get started. So the theme of today's goal is to define the conditional expectation of x given, say, g, to define this object where x is a random variable, and g is some smaller, potentially much smaller sigma algebra than f. So that's today's goal, and you have seen in calculus based probability, you've probably seen expressions of the type the conditional expectation of, say, x given given y is y. You've probably seen something like this. And this is given as you will compute an integral much the same way as you would have seen how to compute. So if you were to compute the expectation of x, right, you would have seen that as an integral over x's values, so that would be over the codomain. So you would have seen that as an integral over, so I should say here, much like, so if you write down what the unconditional ones, there is no conditioning here, so the expectation of x will be like an integral, and then you would have a density. So you would have seen that. So over here, you would do something similar. You would say that this here would be an expectation. So again, you integrate over x's values. So those are in the codomain, that will be up here now. And then you have x, but then instead of f here, you would have to put something else. And so what you would have is you would have f, and then you would condition. And then you would condition, so we should denote the conditional expectation. Many ways to write that, so we can write it as f of x given y is y, and then you would write this here. So instead of integrating over using the density, you would use this conditional density. And so, but this one here can be hard to get, but for example, where if x comma y has a joint density, if you have a joint density, let's call it f, then you would have, you would get this f, this mess up here, f of x given y is y, value at x. You would get this from taking the joint density, f of x comma y, and then you divide out the marginal one. You divide out with the integral. So you'd integrate here over x divide here by y. You need the marginal one here of y. This would be the marginal one of y would be an integral. So you integrate this one up here with respect to x, integrate y. So this is if you have a joint density, you can give meaning to this conditional expectation. But so now what we have up here is going to be that thing. And that thing is going to potentially be more general. This is going to be more general than this one. So our ex of x given g will be more general. But of course must agree with star when there is a joint density. Okay, so our goal is today's lecture is to figure out what this thing here, this object, how we should define it, look at some examples of it, and then of course we have to tie it back to what you're used to when there is a joint density. Okay. See, there are a few more that joined. Are there any questions about the class before we plow into this? This year is going to be, I know this material here, this is going to be challenging. All right, we're not super used to working with sigma algebras, and now we're defining a conditional expectation of a random variable. So keep in mind, this means that it's measurable. It's a function and it's a measurable function. And now we take one of those and I want to define this conditional expectation up here, where you have a smaller sigma algebra. For those of you that are following along in our textbook, where we at is where we at in our textbook is down here. You can see it's called information and conditioning. This here is in the thick textbook. So this is in number 2. So we're down here in this chapter here. And more specifically, what we're going to be spending our time today doing is this section 2.3, the general conditional expectation. And this will take about 10 pages here in the textbook. Okay, so maybe some intuition before we get started on like what could one imagine that this conditional expectation is going to be? Well, as you saw in the headline, right? For us, we think of conditioning as estimates. So this is an important word. We think about them as estimates. Okay, so let's look at some examples. So for example, if x, so this is my random variable, if x happened to be g measurable. So remember what that means. It means that these sets here, these level sets, right? We know that they belong to F because it's measurable, but x less than x, if it happens to be that this is actually inside G for any x in the codomain, well then we're thinking about estimating x given G. What could that be? Right, so now we think, so we want to think about this here as an estimate of x given that we know what's inside G. Right, that's the information. This is G is the thing that we use to decode the information that we have. So let's pretend that we know whatever is inside G. Okay, so if I am in the situation that x is measurable, well then I should know everything that I need to know because x is measurable with respect to G, and this here should give me x. So that's like one extreme. The one extreme is that if the random variable I'm trying to estimate is already measurable with respect to what I condition on, we should just get the random variable itself. And the other extreme being that if I don't know anything, so if G is small, and the smallest sigma algebra we have is the one that just has the empty set and omega in it. So this is the smallest one we have. What do we think then that our best estimate of x is? Well, now I don't know anything. I don't know anything. This is the smallest information that I can cook up. And I don't know anything. What would be my best estimate of x? If I have no information, I'm trying to estimate a random quantity, what would we do? What would be our best estimate? That's right. So the mean value of x, this would just be the expectation. So that's the other extreme. So on one hand, we know x, and on the other hand, we just take the average. But a more interesting case is, so say, this is something we'll come back to, say that x and y, they are standard normals. So I'll write this as the mean being 0 and 0. And the covariance matrix, let's say that the standard normal, so I'll put 1 here on the diagonal, right? And then let's say that there's a correlation. Right, so the adjoint normal, they have mean 0 and they have variance 1, and the correlation matrix, the correlation between them is a row. I x and y are jointly normal. They are zero means unit variances. This is why we call them standard normals. And then there is a correlation and covariance. So that's going to be the expectation of the product. It's going to be rho. This is some number between -1 and 1. Then what? So what is the expectation, say x, given you get to observe y? So now we imagine that there are two random quantities, right? X and Y. We're trying to estimate X. We're trying to estimate X. And somebody tells us what Y is. How would I try to estimate X if somebody tells me what Y is, given that I know that X and Y are jointly normal, and given that X and Y both have zero means and unit variances, and then they have this correlation. Right, so if rho is zero, well then the covariance, then the covariance is zero, which for jointly normals, just see as important, these are for jointly. For jointly normals, if I have a zero correlation, then for jointly normals, this is the same thing as saying that X is independent, right? This is. It's important that the jointly normals is not, this is not working if I'm, this is not working if I'm just normal individually. You have to have this joint normality. So if I have independence, well then what? Then you'll say that X given Y, what should that be? I'm trying to estimate X but I get to observe a random variable that has nothing to do with it. Well, in that case, I should have, well then, I get to observe something that has nothing to do with X. Well, this should be the same as simply just estimating X. Which is zero. But what about the case when rho is in here, but it's not zero? So there's a question up here. Is it the multiplication of the expected values of both? Well, the expectation of each one of them will be zero, right? You have zero means, right? So the expectation of X is equal to the expectation of Y is equal to zero. And the variances, this is the expectation of X squared is equal to the expectation of Y squared is equal to 1. So we cannot, if we take we multiply the expected values, we're just going to get a zero here. And this here is not going to be zero. This is not the conditional expectation is not zero anymore. Here you'll get something, because given that there is correlation, non-zero correlation between X and Y, when you observe Y, you're going to change your opinion about what you think X is going to be an expectation. And of course, in this case here, you actually do have a joint density. Oh, no, sorry, Hoshi. I'm not so good at reading the chat, so this was sort of the previous part. Okay, yeah, so never mind my previous comments. This is not going to be zero anymore, but if you want to figure it out, you could try to use this formula here. Right, so I'm not going to write down the joint density for a multidimensional normal, but if you are so inclined, you can find it in here. And let me just show you on the document camera. Let me just show you on the document camera. So we have two random variables, X and Y. They are jointly normal. If this here is this formula, this is their joint density, right? So it's a long mess. And so what's important to realize is that this correlation parameter that we talked about, this rho, Like this is this row here. So what's important is that you take the joint density, and then you realize that if I take rho to be 0, that means that you have no correlation. So if you take rho to be 0 in this mess, what you're going to get is that the joint density is going to be exactly the product of the two individual normal densities. So when rho is equal to 0, then you're going to get that the joint density is equal to the product of the marginals. And that means that you have independence, right? If the joint density factors into the product of the marginals, then you have independence. But it's kind of, it's very important here for the word, to have the word jointly normal. And indeed, there are counterexamples in here that show that if you just have something like this, like you can have uncorrelated, but you can have dependent random variables. So you cannot take away the word joint. So one thing I would like at the end of today's lecture that you guys would be able to do is to figure out what is this conditional expectation of x given y when they are jointly normal. And, so one way to do it is you will be able to do it using the formula that you have seen probably in some undergraduate calculus-based probability course. You'll be able to plug that mess of a formula we had in here and plow through and try to work out what this expectation in here is, and you'll get the answer. What we're going to do now is we're going to talk about the general conditional expectation, not relying on having a joint density. Okay, so let me pause here, see if there are any questions.
I'm sorry, could you explain the first example where if x happens to be g measurable?
Yes.
Thank you.
So again, here, what we're doing here, this is just intuition, right? These examples here, they're just intuition. This is all heuristic. We don't have the formal definition yet. But what I'm trying to get at is that if we think about conditioning as a way of estimating, I mean, after all, what is an expectation? This is what we estimate something to be. And so when we talk about expectations, we've just been taking the average. So now we're going to refine that notion and say that, well, say that we have some information available, and how is this going to change the way that we estimate x? So the first one is the one where we have a sigma algebra. Like we know x here, so we know that x is if measurable, right? Because it's a random variable. So say that G is a smaller sigma algebra than F, but it still has this property that X is measurable with respect to this smaller sigma algebra as well. Okay, so then how do we think about if I get to observe or know what is inside X, how would I estimate X? Well, if I already know what X is, in the sense that X is measurable with respect to the sigma algebra, well, then my best estimate of X, given that I know what X is, would just be X. So here we know a lot. So here we know X if you have this property. Like, so I'm trying to estimate something that I know. Okay, so if I'm trying to estimate something that I know, my best estimate is, of course, going to be what the quantity is. And this is quite different down here, because here I know nothing. Like, So here we know nothing. Right, so I'm trying to estimate something, and I know absolutely nothing. And then my best estimate is going to be what? It's going to be just take the average. So these are the two extreme cases. Either you know exactly what you're trying to estimate, or you know nothing about the thing and you're trying to estimate. And of course, there's something in between. And a simple example of something in between would be take a pair of jointly Gaussians and condition on one. Does that make sense?
Yes, that makes sense. Thank you.
Yeah. So again, this is all heuristic. So now we're going to do math, right? So this is a math course, so we're going to be precise now. But maybe one more thing. I mean, while we're going through, why do I drag you through the next couple of hours of painful definitions? And well, the problem I'm having is we could try to use the probability of A given B. So this always comes down to something that has to do with Bayes' rule. It's always some version of Bayes' rule. So this thing here, right, this is the conditional expectation of A given B. So what you do is you take the intersection and then you divide by the probability of B. I am sure everybody has seen this. So then the problem we run into is we could try to use this. This is going to be this is our probability measure. Probability measure. Remember, there are two properties, right? The probability measure is it has to satisfy that if I take P of omega, if I take P of omega, I should get 1. Okay, so the first one is I take omega in here, then I'm going to get P of omega intersection with B divided by P of B. This is 1 because the intersection between omega and B, this is equal to B. I divide here by B, I'm going to get 1. And the second property is that if I take the probability of a disjoint union, so let me take a disjoint union here of say say some ANs. I need to do the same. I can plot them outside, sum them up. P of AN given B, right, where AN intersection with AM, this is empty whenever you have two different indices. Right? And again, for example, so let's just do a simpler case. If I take the probability of A1 union A2 given B, how would I compute it? I will use the formula I have over here. So this could be A1 union A2, and then intersection with B. And I can write this as P of A1 intersection B union A2 intersection with B. And then I can use that these two are disjoint. Well, that's because A1 and A2 are disjoint. So I need to divide here by P of B, divide here by P of B. Then I can use that these two sets, they're disjoint because A1 and A2 are disjoint. So this probability of a disjoint union is going to be the sum of the two probabilities. So this will be P of A1 intersection B plus P of A2 intersection B divided by P of B. And now I'm there because this is exactly the conditional expectation of A1 given B plus P of A2 given B. Right? So I have a genuine probability measure, and then I could move ahead and I could say that I want to compute conditional expectation of a random variable given set B. And the way I'm going to do that is going to be by integrating over omega of x, and then I'm going to be integrating with respect to this conditional distribution of here. So I'll write that at P of d of omega given P. Because now I have a genuine probability measure, and so I can use this Lebesgue integration to there I just needed a probability measure to define this expectation, and so I could do that. Well, the problem is, however, for P of this A given B to be defined, we need, what do we need? When can I write the right-hand side here?
PB can't be 0.
That's right. We need this P of B to be positive. Very good. And so keep in mind, what was it we were trying to do here? We were trying to play with something like this. So if I take, so if y is normal, and I'm looking at B, this is my set, what would it be? It would be this set over here. This would be there where y is y. This has probability what? Probability. What do we get when we take a set like that one? What is the probability that a normal is equal to a constant? Y is the random variable, y is normal. What is the probability that it equals 5? So it's answered in the chat. That's correct. It's equal to 0. It's equal to 0. So now we have a problem, because it's absolutely correct that we get a very nice probability measure out in this kind of base analysis. Right? I call it base because it's like screaming. If I do it this way, it's fairly easy to do it the other way too. So you do P of B given A. Well, this is going to be then the same intersection up here, P of A given B, but now we divide by P of A. Right? So you can combine these two. I'll get that P of A given B. P of A given B is going to be that intersection. So I'll keep the P of B downstairs, and then I will move this P of A over here, and then I'll write P of B given A. So there's a connection between condition on one and condition on the other one. And so this is often what's referred to as base rule. Anyway, if that set you're conditioning on has 0 probability, then you have a problem, because then you're dividing by 0 and this is not defined. So that also, that doesn't work. So, which is the reason why when you were taught conditional expectations in this calculus-based probability, then you would always work under the assumption that you have a joint density, and then you can get it to work. So we have this situation often that the sets that we condition on, they have 0 mass, but we don't have a joint density. So what is the general What's the general form? And so this is what we'll do now. When you first see this definition here is it's a little bit like this is basic. This is the general definition of a conditional expectation, and let's have a look at it. So this here is here's the definition. This is of conditional expectation. So a random variable, so a function, I'm going to denote it by e of x given g. So this is a function. It goes from omega into r. So it's a function. This is called, it's called a conditional expectation. Of x given g if, and then there are two properties that have to hold. It's like with the, it's similar to the probability measures and the sigma algebras. Oh, I see a question now in the chat. Okay, so let me answer that question before I write down the definition. Yeah, so what's the probability? What's the probability of a standard normal assuming the value is 0, or assuming the value y? Well, one way to see it would be if you look at a picture, as I say that y is down here. So you have your dome. This is the density dome. So I have my y sitting here. I'm looking at some interval around it. And then I can move this interval closer and closer to y. So if I look at sets of the form, we've had these sets before. If I look at y, and then if I subtract a little bit, y 1 over n. This here could be my this could be my set. So I'll have, if I am to write the set y is y, I can write this here as what? That's the same thing as saying that y belongs to y minus 1 over n y. And then I'll have to take intersection over n's. Like the only point that survives in here is going to be the y that you had to begin with. So that was my little picture up here, but maybe I should blow it up a little bit bigger. So I have a y here, and so what I do is I take a set y minus 1 over n, and then as n goes to infinity, this thing moves over. And when we know that the probability by the monotonicity of measures, this is equal to the limit as n goes to infinity of the probability that y belongs to these other sets. And what would that be? This would be the limit. And since here you get this n evaluated at y minus n evaluated at y minus 1 over n. And that would be 0. Okay, did that answer your question? The question in the chat, could you follow the argument here? Okay, so this sort of decomposition, we have seen that for the Borel sigma algebra, and we've talked about that probability measures are monotone. So if I have a sequence of sets that either increase or decrease, I can compute the limiting probability, simply by taking either the intersection or the union of these monotonically decreasing or increasing sets. Here they are decreasing, so I'll take the intersection. The limiting probability is going to be the probability of that intersection over here. Okay, we compute them, and you get a 0. Right, so this is much more general. This holds whenever you have a density. This works for all. This works for all random variables. For all random variables with a density. It has nothing to do with particularly normal. So when you have a random variable that has a density, then the probability of that random variable, assuming any given value, is going to be 0. Okay, so this is what it looks like then. So let's go back to that definition we were trying to get at here. So make this page 6. So conditional expectations, I take a random variable x, right? So x is going to be f measurable. And I'll take a smaller sigma algebra. I denote that smaller sigma algebra by g. G is inside f. This is called, this expression here, this is called a conditional expectation of x given that smaller sigma. If it's what? It's a function, so it goes from omega into r, and it satisfies two properties. One, it's g measurable. Right, so this function here is g measurable. Right, so what that means is that if I look at the level sets, the conditional expectation of x given g, this is less than x. Pick something over in the codomain. This is going to be something in g for any x. So that's the first property. It has to be g measurable. And then the second property, this is the one that is kind of difficult to wrap your head around, at least here in the beginning. It's what's referred to as the partial averaging property. The partial averaging property. What does that mean? It means that if I integrate the random variable x with respect to the measure p over anything in the sigma algebra, so that's a little g, I get the same thing as if I integrate not the random variable x itself, but the conditional expectation of x given g. And this has to be true for any set in the sigma algebra that you condition on. So there are, so often you will see you'll see 2 written as instead of writing these integrals, you will see it written as expectations. So you will see an expectation of, and then the indicator for g times x, that this is to be the same as the integral, the expectation, the indicator, and then the conditional expectation. So you see this statement instead. So there are 2 properties that you need to check if you want to verify that a random variable. So now it's a random variable because it's going to be measurable with respect to g. So, and g is inside f. So in particular, this is going to be f measurable. So it's a conditional expectation as a random variable that happens to be g measurable and satisfies this restriction here that when I integrate the random variable, that conditional expectation, I'm going to get the same thing as when I integrate the random variable x, the original one, over subsets in that sigma algebra that I'm conditioning on. So this is kind of a lot to take in. That's the general notion of a conditional expectation. So when you see this written out, and you're thinking back to your class that you had, the calculus-based probability class, right, where you were studying, here's also a conditional expectation, right? And it's given by this formula, and so on. Like this conditional expectation here that you had in your calculus-based probability, it must be the case that it also satisfies properties like 1 and 2. Because if it didn't, it would be inconsistent. So we are basically in the same situation that we were in last time. Namely, we had this abstract Lebesgue integral. And if we specialize to the case of densities, that abstract Lebesgue integral had to become like a standard Riemann integral. So we need to check stuff like that for this conditional expectation here as well. Okay, so what we're going to be doing now is we're going to be working with this definition. So we have the two properties. So what we're going to be interested in is existence and uniqueness of this object. So existence here, this is really hard. And this one here, the uniqueness part, this is not too hard. No, those are the mathematicians care about that, right? So we have a conditional, we have this abstract concept of a conditional expectation, and is given in terms of these two properties. So one can ask, does there exist such an object? And if one exists, is it unique? And I mean, you can already guess what the answers are, namely that yes, it exists, and yes, it's unique. Because otherwise, this would not be a very good concept to work with. So we need to establish these two properties. Existence, this is really hard, and the way that we're going to do existence is using a theorem that we're going to be needing in other contexts as well. This is the Radon-Nikodym theorem for changes of meshes. And changes of meshes, this plays a very large role in quantitative finance. We already talked about the measure P, and we already talked about the measure P tilde and how they're linked. And so that is all a special case of Radon-Nikodym's theorem. So we'll use that. We'll talk a lot about Radon-Nikodym later today. So this is the existence part. The uniqueness part, this is not so bad. So I propose that we start out with the thing that is not too bad. And so we'll do the uniqueness. So for uniqueness, we'll do that first. For uniqueness, let y satisfy 1 and 2. And then we show, then we'll have that y is equal to the conditional expectation of x given g. Then we will show that d are the same, and this is with probability 1, right? Remember what this here means? It means this means that the probability that y is not equal to the expectation of x given g, this is equal to 0. Remember, that's what this almost sure means. That the set where it doesn't hold, the set where it doesn't hold has zero probability. Okay, how are we going to do it? We're going to take, we're going to look at where one is bigger than the other. So if I look at the set A, this is going to be those omegas where y is, say, bigger than the conditional expectation. Then what I'll do is I'll say that y is G measurable, the conditional expectation of x given G is G measurable. So this here is going to be a set in G. This here uses property 1. And then we can use property 2, because give me any set inside G, I know that this here holds. I know that the left-hand side is equal to the right-hand side when I integrate over sets inside the sigma algebra. So I'll get that. What will I get? I'll get that the integral over the set A of y with respect to the measure P, this is the same as y was given to satisfy 2, so this is the same as integrating x over that set. And of course, this is going to be the same as integrating the conditional expectation over that set. So this was 2. So then I take a difference. So this implies that if I take the difference, I'll have y minus and then this stuff over here. This is 0. So what can I then say? I'm looking at a set A. I'm integrating this thing B, and I get 0. What is A? A is a set where y is strictly bigger than the conditional expectation. And so here I have exactly that difference. So on the set A, that difference is strictly positive. What does that tell me about? What does that tell me about A? So again, if I'm looking at, I have my set A, this is when y strictly dominates the conditional expectation. So now I have an integral over that set of that random variable, and on that set, that random variable is strictly positive. What does that tell me about the set when I know that the integral is 0? The integral is 0 because inside the integral I am strictly positive. That's correct. This here is exactly 0. Okay, so that means that this set here has probability 0. And of course, there's nothing special about picking y strictly positive. I can also pick it to be less than. So I can do the same thing. A similar argument. Shows that the probability of y being strictly less than the expectation of x given g is 0. So uniqueness holds. Uniqueness holds. If I have 2 random variables to satisfy 1 and 2, these two random variables will agree with probability 1. Okay, so this was a part that was not too hard, and existence, this is much harder. Okay. So now we're going to turn to existence. So for the existence part, the existence part uses a this is a big gun. This is called random Nicodim theorem. Okay, so we're going to be talking about random Nicodim's theorem for a while. When you see it discussed the way that I'm going to do it, you might wonder, like, what does that have to do with the existence of conditional expectations? And this is true. It's not obvious from the beginning that this theorem here has something to do with conditional expectations, but it really does, and then we'll link it up later today. So Random-Nikodim's theorem, this has to do with change of measure. Right, so we're going to talk about, right, so we have, so on F, we have P, and on F we have P and say another measure that we call it Q. You're both probability measures. Okay, so on the sigma algebra, we have two measures now. So we say that one, P is absolutely continuous with respect to P is absolutely continuous with respect to Q if what? If Q on a set A is 0 implies that P on that set is 0. So a probability measure P is said to be absolutely continuous with respect to another one if this one measures a set A to be 0 implies that this is the other one is 0. And we write, in which case we write P and then these two things, these two less than or equal to after each other. So that's just notation. This symbol, it means that implication here. So first we can swap P and Q's roles. We can swap P and Q's roles. We say that Q is absolutely continuous with respect to P if, and then what you write is P of A is 0 if that implies that Q of A is 0. In which case we write, and then we swap P and Q. And then third and finally, P and Q are equivalent. P and Q are equivalent if P is absolutely continuous with respect to Q and Q is absolutely continuous with respect to P. Any questions on this part? If not, I want to look at an example. And we try to see if I can get it big enough. Can you guys read what's on my little sheet of paper here? We see it?
No, it's not really that clear on my end.
Yeah. Okay, I'll have to write it out by hand. But this is one of the problems that, well, it's an old exam problem. So it's one of these problems that we'll use for the old exam later this month. So let's do an example. Just to put this abstract discussion into context. Okay, so this is an example. This is number 16 on the exam, on the old exam question sheets. So this is number 16, and we say that, so you have a random variable. You have a random variable, x goes from omega into r, and we assume that the distribution of x under a measure P is standard normal. So this is given as you integrate out in the normal density. And then what do we get here? E to the minus y squared over 2 dy. This is for any x. And on the Q, the random variable x is equal to, well, first off, it's equal to 0 if x is negative. And it's equal to, say, an integral from 0 to x of e to the minus y dy when x is positive. All right, so this here is the normal. And this one here is the exponential. So we can ask these questions like, are these measures, are they absolutely continuous with respect to each other? Is P absolutely continuous with respect to Q? Q absolutely continuous with respect to P? What do we have? So do we have, this is the first question. Do we have that P on a set A being 0 implies that Q on that set is also 0? Okay, so let's try it again. So we have a random variable. We assume that under the measure P, all right, so we have a random variable and we have two measures, P and Q. We assume that this random variable under the measure P has the standard normal distribution, whereas under the measure Q, it's exponential. So these two measures, we can then ask the question, do we have properties, do we have the first property, do we have the second property? Right, so we start out asking, is P absolutely continuous? No, is Q absolutely continuous with respect to P? This is this question here. If P is on the set is 0, is Q on that set also 0? That means we're asking if Q is absolutely. All right, so there's a question there's a comment in the log. So what is, if X is equal to 0, then P of A is 0 and the other one, then P of A is a half and the other one is 0. Okay, so we're looking at a set now. We're going to try set A. The set A is going to be when X is less than 0. Okay, and then if I take that one, I put it into P, then P of A is a half. Yes, I agree. And Q of A is 0. Okay. So that means also that, I shouldn't say means, that implies that Q of A is being 0 does not imply that P of A is 0. So which one is that? Is that the one we were going for? Okay, so P is absolutely continuous with respect to Q. If Q on that set being 0 implies that P on that set is 0. Okay, so we have, so what do we have? We have that P, we don't have that, right? So we don't have that. Okay, yeah, I agree. But it's not quite the one we were going for. Like we were going for this implication. If there is nothing to be seen under A, is also nothing to be seen under Q. So this here was question 2. This was question number 2. What do you think about? What about the other implication? What sets does the measure P see? Yeah, be careful about, so the suggestion in the blog, in the log says that we should consider singletons, single point sets, but be careful about that because they are always null sets. Right, the point here is that there is a very large set. There's a very large set here, and it's like that's this set here has lots of points in it, but the Q measure simply doesn't see them, whereas the P measure does see them. But in the case of the in the other one, the measure P sees everything. So that means that if the measure P, if there's a set that the P measure doesn't see, then Q will also not see it. So do we have this? And so here the answer is actually yes. And okay, so how do I formally do this? So yes, and this here uses the Radon-Nikodym derivative. Okay, so let me try to explain that a little bit more. So we're good on, we don't have the other one. So two is no. And the first one is a yes. Okay, so what is a Radon-Nikodym derivative? This is actually precisely what is being asked in that question number, that problem number 16. The first question says, do we have this absolutely continuity property? And if the answer is yes, please provide this Radon-Nikodym derivative. Okay, so a random variable so we're going to be denoting it by dq dp. A random variable dq dp is called a Radon-Nikodym derivative if what? If I can write Q on a set A as an integral over A of this random variable dq dp, integrated with respect to P. And sometimes you'll often see this written as an expectation of 1A and then dq dp. So the way that you've been asked to figure this, the first question, the thing you've been asked here is to provide this Radon-Nikodym derivative. That is, you've been asked, so your job is to find, your job in 1 is to find this guy. And given that we only have one random variable, this we're going to write this here as a function z of x. Right? This is a random variable, so we're going to make the guess that this is probably equal to a function. This is probably equal to a function, or a function z going from to the positives. Okay, so can we find such a function? Yeah, it's not terrible. You look at the defining property. A random variable, this is called a Radon-Nikodym derivative. A random variable, this is called a Radon-Nikodym derivative. If I can express that top measure in terms of an integral with respect to the measure that appears at the bottom. So what we want to do is we want to look at q of x less than x, and then we want to write this here as an expectation of the indicator, and then my set is x is less than x, and then dq dp. And we're hunting this function z here. So I'll write this out as an expectation indicator x less than x, and then cx. We're looking for a function such that the Radon-Nikodym derivative is given as that function composed to the random variable x. And then we'll write out what is this thing here. This is an expectation. I can write that as integrals. I can write that as integrals. I can write that as integrals over the codomain indicator. I replace the random variable x with a dummy, so we call it y. Y is less than x. Zy, and then I have to multiply into x's density. X's density was up here. This is 1 over root 2 pi integral 1 over root 2 pi integral, and then you have e to the minus y squared over 2 dy. And of course, on the other hand, I'll have that this thing here is equal to either 0. This is when x is small, and is equal to this integral from 0 to x, e to the minus y dy when x is big. So I have on the left-hand side, I have this expression. On the right-hand side, I have this expression. My job is to find a function such that this matches up. Okay, so the first thing, this indicator, I can move him over to an integral over the axis here. So there's going to be an integral. Instead of integrating over r, I'll integrate y's from minus infinity to x. Then I'll have my z of y, 1 over root 2 pi e to the minus y squared over 2 dy. What should I pick for my function z? Well, I'm going to match what I have here with what I have up here. So for x negative, what are we going to set? What are we going to set z of x to be? So we're going to break it up into two points. Maybe I shouldn't call it x. Maybe this is unfortunate. So I put y here. What do we want how do I get it to match up? How do I get it to match up when the variable here is negative? Well, then I'm going to be looking at z's evaluated at negative points. Yeah, I see it in the log. This is correct. We're going to put it to be 0. We're going to put z of y to be 0, and then for y positive, we're going to set z of y to be, what should it be then? Well, then we match up, right? Because if I'm 0 all the way up to the integrand, here's going to be 0 now from minus infinity up to 0. So then I just want to solve. Have the integral from 0 to x e to the minus y dy. I can now integrate from 0 upwards to c of y 1 over root 2 pi e to the minus y squared over 2 dy. So we want these two things to be the same. So take the derivative, and then that will give me e to the minus y has to be the same as c of y 1 over root 2 pi e to the minus y squared over 2. And so I solve that I get that c of y, this is e to the minus y root 2 pi e to the what? E to the no, not minus, this should be plus y squared over 2. Right, so my Radhanickel derivative so the Radhanickel derivative, this is this is the dq dp, this is equal to z of x, where c of y is a function is equal to 0 when y is negative. It's equal to this mess up here, e to the minus y, e to the y squared over 2 root 2 pi, and this is when y is positive. So this was new concepts here in an example. We were given two measures, P and Q, having these. So we have a random variable that has normal on the one and exponential on the other. Quite quickly we figured out that we do not have equivalent measures. We only have at most one that's absolutely continuous with respect to the other. Okay, so then the goal was, can we create this Radhanickel derivative? And we did so. And here's a specific representation of the Radhanickel derivative. And so if we turn it around, if we try to do this in the other case, if we try to do this in the case that was suggested in the log, where did my page go? Where did my page go? One of you said that this was not possible. We should look at this. If we try to do the same thing, but swapping the roles of P and Q, then apparently we're going to have a problem. So if we try to do that the other way around, if we tried to construct instead of dq to p, we will construct dp to q. We will run into problems. So how would we try to attempt? What would our attempt be? Well, we would swap the roles of P and Q. Okay, so now on the left-hand side, instead of Q, I would have my P. So here I would have P of X less than X. And I wanted to write that as an expectation on the Q. Okay, so I'll do the same thing. I'll write this as an expectation on the Q of the indicator that X is less than X. And then I'll write here dp dq. And now why would that be a problem? Like, this is what we want. Proceed as before. Write this here as an expectation on the Q of an indicator X less than X. And then this Radhanickel derivative, we write this as, like, say, C, and now this will be a different one. we need a different symbol. Maybe we can call it for C bar of X. We write this here out as an expectation. So we can write this out as an integral. The indicator, and then I replace the random variable by its dummy. So this is less than dummy less than X. We have this radical derivative that we're trying to create. And this would be a dummy, so that should be Y. And then we multiply onto the density. And we multiply onto the density. We multiply onto the density of under the measure Q, and this was the exponential. This was the exponential. This would be the when I am under Q, I'll have the exponential, so I'll have to integrate from 0 to infinity. I have to integrate from 0 to infinity, and then I would have e to the minus y dy. And the left-hand side in this case now, well, this is going to be the Gaussian. So that was the Gaussian. This was 1 over root 2 pi. And then an integral from minus infinity to x of e to the minus y squared over 2 dy. And what I'm doing now is I'm trying to get at, can I get this to work? Well, as before, we can move the indicator. We can move the indicator on the x-axis. So I'll have to integrate here from 0 to x, z bar of y e to the minus y dy. So can I get this? Can I get this to work for all x's? Well, we're saying here that if we try to do it, we would run into problems. And so, what is the problem? Why can I not do? Why can I not do what I had here? Well, when is this valid? This here is valid. This here is valid provided that my x here is positive. This here is when x is positive. Otherwise, I'm going to get 0. So then, if I'm looking at, if I plug in, what was it that was suggested by Boucher? The thing that was suggested was to consider this spatial number 0. This was the threshold x that was being proposed. And so if you take that number and we plug it in here on the left-hand side, I take my little x to be 0. If I take my little x to be 0, then on the left-hand side, I'm going to get, well, a half. And on the right-hand side, if I take x to be 0, on the right-hand side, I'm getting a 0. So, or I can say, but x being 0 gives 1/2 equals to 0. This is impossible. So we cannot do that. What this exercise here is getting at is that there seems to be a connection between the ability to create radical derivatives and this absolute continuity property. And this is exactly true. This is what we're seeing is examples of the Radon-Nikodym theorem. So this is the big result that we need. This is Radon-Nikodym Radon-Nikodym's theorem. It says that Q is absolutely continuous with respect to P if and only if and only if there exists a random variable dq dp dq dp. So this is a random variable that goes from omega into the positives such that when I compute the probability of a set A under the measure Q, I simply do that by integrating Q to P. So this was that formula we had before. So two measures, Q and P, we have a radical derivative if and only if Q is absolutely continuous with respect to P. And then just one thing to note, if I take A to be omega, well then Q of omega, this is a probability measure, right? So on one hand is equal to 1, and on the other hand is equal to the expectation of 1 omega times the Q to P. So this is just the Q to P's expectation. So that radical derivative, excuse me, that radical derivative that we're getting here is a positive random variable, and it has expectation 1. Yeah, so so now there's a really good question in the log. Yeah, this is exactly what it is. This is a generalization of I mean, this theory we're doing here, this is a generalization of the calculus that you're used to. So this the Q to P here, yeah, this has ties with the Jacobian. I think we should take a little break here, try to think about this, and then after the break, I'll do one more example of a radical derivative, and then we can get some more questions. So let's take a little 10-minute break. Remember, we always have to switch over to a different Zoom link. I will see you 10 minutes from now.